So a power series actually is an infinite series of power functions. Okay, because you know for each terms here, it is the nth power of this difference. So it's a function of z. Okay? And z0 here is a fixed complex number, and we call the center of the power series. And we have a sequence of constant numbers, c sub n. C sub n will be called the coefficients of the power series. So, so basically, it's an infinite series of functions. Okay? Functions. Before we give some convergence conditions, this definition is just a formal definition. Okay? So we just say that it's just an infinite series of power functions here. And so if we do not mention the center, okay, and then we just assume the center is 0, it is the origin of the complex plane. Okay, so but once we have a non-zero center, we have to mention that. Okay, so here the center is z sub 0. All right. So suppose we are given a power series. Right, so z sub 0 is the center of the power series, and we have c sub n's or coefficients. And then we let so the coefficients, they form a sequence, right? A sequence of these numbers. So we let alpha to be the input of this sequence. So the sequence is derived from the coefficient sequence by taking the nth root of the absolute value, all right, of the nth coefficient. Okay. So this is a sequence, and we take the input of this sequence and say it's alpha. So alpha always exists, okay? Alpha always exists. And it's possible that so alpha, I have to, alpha is in from 0 to infinity, including the infinity, okay? But it's possible. So let's say that. Now, then, in the power series, okay, the power series converges absolutely if z minus z0 has absolute value less than 1 over alpha. Okay? So we know that the power series converge absolutely if the z, right, is not far away from the center, right, and the distance, the distance should be less than 1 over alpha. So alpha is here, right? This is the convergence part and the convergence part, and divergence if the distance is greater than 1 over alpha. Okay? So 1 over alpha is a threshold, okay, to indicate that the power series, all right, whether it is converged absolutely or it diverged. So the proof is by using the root test. Okay. All right. So now. Now for each choice of z, okay? Then we have, so we fix z, all right? So we choose z from the complex plane. Then the infinite series of complex numbers. Okay, so we just substitute a particular choice of z so that this comes to a complex number. Okay, as complex number, this is come to an infinite series of complex numbers. So this infinite series of complex number converges absolutely right if the result of the sequence of its terms. So the sequence is that the term is Cn z minus z0. Okay. Okay, yeah. So if the result is less than 1, and diverges if the result Cn z minus z0 to the nth power, take the absolute value. Okay, so that's just the term here, right? Is greater than 1. So by the root test. Okay, so the root test gives us this test according to the threshold 1 here. Okay, so you have that. Now we take a look at that. So, so for here, so what is this? This is equal to z minus z0 and n cn. Okay. So this term actually is equal to the distance of z to z0 times, all right, this quantity here. But this is fixed. So the result. So actually, so this is going to be, so from here, so we can see that this is even only if the result, okay, and okay, less than 1 over EC. Okay. And but here, this is going to say that result greater than 1 over z minus z0. Okay, but as we know, the result here is defined to be alpha. So this is alpha. Okay, so this is if and only if alpha is less than them, so this is z minus z0 less than 1 over alpha, or z minus z0 greater than 1 over alpha. and then so we have done. So if the distance is less than 1 over alpha, then this series converges absolutely. But if it's greater than 1 over alpha, then the impedance series diverges. So this is the proof. So the number of the 1 over alpha is called the radius of convergence. Alright? ROC of the power series. Okay? So we can, just suppose the center is here. The center is here. And now with radius, which is rho is 1 over alpha. So now within this disk, in this disk, when Z is in this disk, then the power series converges absolutely. But outside the disk, oh, outside of this, the power series diverge. On the boundary, we don't know. Okay? So you have to check. If a point is on the boundary, then you have no conclusion. You have to check every point on the boundary. Okay? You have to check that. So this is the situation. Any power series is convergent behavior. They have the same phenomenon, right? Either it converges absolutely within an open disk with center Z0. Z0 is just the center of the power series. Okay, and the radius is just the reciprocal of the insert of the square root of the absolute value of its coefficients, alpha here. Okay. And outside the open disk, okay, outside the open disk, or you can say outside the closed disk, okay, not including the boundary, the power series diverge. Okay, they diverge. So it's a general phenomenon. Any questions? Okay. Okay, so now from the theorem, you can see that the computation of the insert is very important. Okay. So you have to build your ability to compute the insert, like this one. All right. So there are some consequences presented in this theorem in the textbook. I just stated every power series, okay, converges at its center. Why? Yeah. Because that when z equals to 0, here all the terms except the constant term to be 0. So it is equal to c0, right? So it's quite simple. If a power series that converges at a point z equal to z1, which is not equal to the center, okay? Right? It converges absolutely for every z closer to the center than z1. Okay, that is z minus z0 is less than z1 minus z0. Okay, so if we know z1 is already a point such that the power series converges absolutely, then you know the z1 should be here. z1 should be here, okay? And at any point, right, closer to z0 than z1, right, must be also inside the open disk. So of course, this is true, right? If you know the behavior like that. So the second point, of course, is, okay? The third thing is, if a power series, right, diverges at a point z equal to z1, that is at the center, then this power series diverges, okay, for every z, okay, farther away from z0 than z1, i.e. if z minus z0 is greater than z1 minus z0, then this z, right, then the power series must diverge at this z. So the situation is here, if z1 is here, then anything further away from z0 would diverge. Okay. So this theorem is the simple consequence of what we get here. Okay, of course we can use the ratio test too. So here is theorem. So suppose that a power series with Cn not equal to 0 for all n. Okay? So suppose we have a power series such that the coefficients never 0. Okay? Never 0. And assume the limit exists, the following limit. Okay. So the coefficients, so this is the limit exists. Okay. then the power series converges absolutely if z minus z0 is less than 1 over alpha and diverges if z minus z0 is greater than 1 over alpha. Okay, so you can use the ratio test here. Okay, the ratio test. Okay, so I just mentioned the statement without proof because you can see the proof in my lecture notes. It's quite simple, just apply the ratio test. And it is strong. It is strong. Why? Because it requires that this ratio, okay, the aspect of the ratio has limit. Okay, so it is very convenient, but in many situations it is much more easier to compute the alpha here. It's much more easier to compute the alpha. But if you encounter a power series such that this sequence of ratio does not have any limit, then you have to use the theorem 15.2.8, okay, to find the solution. Okay, to find the solution to solve your problem. Okay. All right. In my supplement, I give actually quite a few examples. Power series and alpha and rho, right? So this is C. Consider, right? Consider this power series with center 0, and the alpha here, the lim sup, okay? So lim sup n to the nth power. So it's n to the nth power. Okay, lim sup. Now the lim sup is equal to lim sup, and this is just n. Okay, so when n goes to infinity, this is infinity. So the rho, all right. So rho is equal to 1 over alpha. Becomes 0. So that means that this power series converges just at the center at 0. Okay? And diverges any other point. Okay? So, and the ROC, the radius of convergence, is equal to 0. The other example is factorial, and as you may notice that when you study the exponential function later, actually this is, I would say this is exponential function, but we'll see that later. Actually, this one, so lim sup and go to infinity. N factorial is 1 over n factorial. Okay. Okay. So if we want to choose this one, we find that it is quite hard, right? Quite hard. So instead of that, we use the ratio test, right? So we have 1 over n plus 1 Victoria, 1 over n Victoria. Okay? So we use to see if the limit exists, right? And so the limit, we find that this is equal to 1 over n plus 1, so it's 0. So indeed, the limit exists. Okay, and so the rho is infinity. So that means that this power series converges everywhere in the complex plane because the radius of convergence is infinite. Okay. So this is the question. Right? So you see that in this case, and in many different cases, that the use of ratio test is quite convenient. But as I say, you have to find the limit. Okay, find the limit to see if it exists. The ours is 1. And you have boundary point, right? On the unit circle, you have to check. You have to check. And so in here, okay, if z equal to 1, if z equal to 1, we have okay, so to eliminate some, so we start with 1, I'm sorry, not from 0. Okay, and so this is the harmonic series, and we know this is infinite, right? Okay, so we know at z equal to 1, the power series diverge. Okay, so it diverges. But for any other z with modulus equal to 1, the power series conditionally converges. Why it does not converge absolutely? Because when you take the absolute value, then the absolute value is equal to 1, right? But we already show that if this is 1, then it's divergent, right? So it's possible. So for other z, right, for other z, the power series does not converge absolutely. But it converges conditionally. You cannot take the absolute value, okay? Cannot take, but just original form. So if z is other kind of things, okay? So that means that, let me say it. Okay? Maybe t, okay, right. And t is in 0 to pi, okay, so in this interval. So for any t in this interval, the sequence, this infinite series will converge conditionally, okay, it will converge. And the proof is given in my supplement, so please take a look. But quite technical to prove that. When t is equal to 0, you get this one, harmonic series, so it's divergent. But if t is not equal to 0, just from 0 to 2 pi, for any t, okay, then this is series converge. Okay, conditionally. Condition means that not absolutely. Okay. So it's usually hard to investigate the convergence property on the boundary. Usually hard. Okay. And I also give a very interesting example. So another example. Find the ROC of the power series summation. Okay, so to find ROC of this power series actually is to find the lim-sup, the alpha, okay? The alpha. And you can see that this sequence does not converge, okay? So we have to so the solution is the illustration. So we will use the exponential. Note that because in section number 1, I developed some of the properties, right, for you to compute the lim-sup or the im. Okay, so these are techniques. And in power series like this one, you need that kind of technique. Okay, to find the lim-sup. Okay, so this is just illustration. Note that the function, the exponential function, right? It's a monotone increasing function on the real line. Okay, so we will use this function, and we know it will behave. So it's monotone increasing and continuous, of course. But the point is that it's monotone increasing in consequence. So to find the lim-sup, the alpha, right? So we try to find the lim-sup. So the lim-sup is here, okay? 1 minus. Okay, so this is one. And the coefficients is always non-negative, so we don't need to put the absolute value, okay? The absolute value sign, we don't need to put that. So just like this one. All right, now, okay, so we will say that we will take the lim-sup, right? And we will take the logarithm as well as exponential. So this is become exponential of the logarithm. Right? Exponential of the logarithm of here. Okay? The reason why we want to use logarithm because to alleviate the burden of the nth root. Okay? To alleviate the burden of the nth root. Okay, so the alpha is something like this one. Okay, so and because exponential function is monotone increasing and continuous actually, so the lim-sup of the function of something becomes exponential of the lim-sup n goes infinity limit. And the limit, and now this time I can write down is 1 and Okay? Or something like that. So once we find the lim sup of the exponent, we take the exponential function, we get the alpha. Okay? And this one is much more easier to deal with. Okay? So I use this transformation. Okay? All right. So now, so we will use the definition of lim sup. What is lim sup? Well, we know lim sup of right is what? It's the limit, right, of m goes to infinity, and the sup for all n greater than or equal to m, so maybe m for n goes to infinity. Okay, so lim sup is that we take limit of the suprema of what? Okay, so we take this is the meaning of lim sup. Okay, so we take the suprema for m greater than or equal to n. Okay, because the suprema always exists. Okay, suprema is just the this upper bound. You know that this upper bound, right, of this sequence, right? And as n go up, you know the suprema going down, right? You know when n go up, right? You have less m, right, to take the suprema. Right? So as n go up, the sup go down. So as a function of n, this is the decreasing function, decreasing. Okay, any decreasing function and low bounded by 0, right? Should have a limit. The limit always exists. Okay, so this study, all right, and so we find, okay, so this one defined to be an, okay, to be an. All right, so now look at an. So an by definition, actually this is equal to, we have 2 log 2 plus 1 over 2n. If n is even, okay? So when n is even, we have here, and if n is odd. Look at here. The sum of the first two terms is either 2, 0, 2, 0, right? It's alternating. But the third term is exponentially decreasing as n goes up. Okay? So this is all goes up. All right, so you see that if n is even, all right, the first term would be the biggest term, right? The first term. So when m equal to n, this is the biggest term. So we have that. But when n is odd, because when this is odd, we have 0 plus something, right? So it's not the base. Actually, the biggest term is this term. The next one, because n plus 1 is even. Okay, so we have that. So the an has 2 values here. Okay? But anyway, as n goes infinity, this goes to 0, but this one is go to what? Log 2, right? So this has limit, this also has limit, right? So you have 2 sequences, each has a limit. So the product of the 2 sequences actually And take the actually is the product of the limit in each sequence. So this go to 0, this go to 2. So now, so the limit actually, we know this limit, an, right, is equal to 0. Okay? So this is 0, right? And alpha is exponential to 0, so it's equal to 1. Okay? And so the ROC is equal to 1. Like that. Okay? So the metric seems like we use the exponential function, right? To either, because the square root of n is quite difficult to deal with, so we usually take the logarithm. Yeah, but actually we have to recover it, so we use the exponential function. Okay, and because exponential function is a monotone increasing continuous function, so that with the property actually is in section 1, right? 15.1. You can see that, right? And so we deal with here this term, and use the definition of the insert. Okay, so we examine the sequence behavior, and we find that eventually this insert is equal to 0. So alpha actually is e to the 0th power equal to 1. Okay, so this is how you learn to compute the ROC. Okay, and so it depends on your ability to find the insert. Okay, so this is quite important for you. Okay, so let's take a short break for 5 minutes.